Hello everyone, today we will study the chain rule. The chain rule for multivariable function has different cases. Let's look at the simplest case first. Case 1. Only one independent variable. Let z equal to f of sy. Let x be the function of t. Let x be a function of t. Let y be a function of t. Then I can write z as a function of t. Then I can write z as a function of t. That equal to f of x t comma y t. And this t is called the independent variable. Both s and y depends on t, and z depends on s and y. This t is called independent variable. In this function, there's only one independent variable called t. This is the case with only one independent variable. At t equal to t0, let x of t0 equal to a, let y of t0 equal to b. Suppose x of t and y of t are differentiable at t equal to t0, and f of sy is differentiable at t at sy equal to a comma b. Then chain rule says z of t is differentiable The chain rule says z of t is differentiable at t equal to t0. If you treat z as a function of t, then z of t is differentiable at t equal to t0. And z prime of t0 equal to the partial derivative of x a comma b times x prime of t0 plus f sub y of a b times y prime of t0. And this equation can be rewritten as dz over dt equal to delta f over delta x times dx over dt plus delta f over delta y times dy over dt when t equal to t0, sy equal to ab. This formula is called the chain rule. Now let's try to prove this formula. Let's try to prove it. First of all, let me recall the definition of differentiability first. Since f of sy is differentiable at sy equal to ab, by definition of this differentiability, there exists epsilon 1 and epsilon 2 such that f of sy minus f of ab equal to f sub x of ab times s minus a plus f sub y of ab times y minus b plus epsilon 1 times s minus a plus epsilon 2 times y minus b. Where epsilon 1 and epsilon 2 approach to 0 as the point sy approach to AB. That's the definition of differentiability that we learned last class. That's the definition of differentiability that we learned last class. Since I treat x as a function of t, y as a function of t, and a equal to x of t0, y equal to b equal to y of t0, so this equation can be rewritten as f of x t y of t minus f of x of t0 y of t0 equal to f sub x of ab x of t minus x of t0 plus f sub y of ab y of t minus y of t0 y of t minus y of t0 plus epsilon 1 times x of t minus x of t0 plus epsilon 2 times y of t minus y of t0. Next, if we observe this equation, we can see that f of x of t, y of t is equal to g of t. So this is g of t. And similarly, f of xt0, y of t0, that's g of t0. So this equation can be rewritten as g of t minus g of t0 equal to f sub x of a b x of t minus x of t0 plus f sub y of a b y of t minus y of t0 plus epsilon 1 x of t minus x of t0 plus epsilon 2 times y of t minus y of t0. Now, if I divide both sides by t times t minus t0, what do I get? If I divide both sides by t minus t0, I have g of t minus g of t divided by t minus t0. If I divide both sides by t minus t0, I have f sub x of a b times x of t minus x of t0 divided by t minus t0 plus f sub y of a b times y sub t minus y sub t0, y of t minus y of t0 over t minus t0 plus epsilon 1 times x of t minus x of t0 over t minus t0 plus epsilon 2 times y of t minus y of t0 over t minus t0. Next, I take limit. Take limit on both sides as t approach to t0. Next, I take a limit on both sides as t approach to t0. Next, I take a limit as t approach to t0. I have g of t minus g of t0 over t minus t0 equal to f sub x of ab. That's a constant. I leave it the way it is. Take limit t approach to t0. X of t minus x of t0 as t approach to t0. And again, this is a constant. F sub x, f sub y of ab is a constant. Let's f sub y of ab times the limit t approach to t0 y of t minus y of t0 over t minus t0 plus limit as t approach to t0 epsilon 1 times the limit as t approach to t0. Here epsilon 1, epsilon 2, they are not constants, so I need to write limit, keep limit here. Limit t approach to t0 epsilon 1 times limit x of t minus x of t0 over t minus t0 plus, since the epsilon 2 is no constant, I need to write limit as t approach to t0 epsilon 2 times the limit as t approach to t0 y of t minus y of t0 over t minus t0. I take limit on both sides. Take limit on both sides. Next, this limit here, when t approach to t0, g of t minus g of t0, t minus t0. This limit is g prime of t. This by definition of derivative. This limit is g prime of t equal to f sub x of a b times this limit is this limit is g prime of t0 times this limit s of t minus s of t0 over t minus t0. This limit is x prime of t, s prime of t0. This is derivative of x at t0. This is s prime of t0 plus f sub y of ab is a constant. this limit as t approach to t0, y of t minus y of t0 over t minus t0. This is y prime of t0. Look at this limit here. T approach to t0. As t approach to t0, as y approach to ab. As t approach to t0, as y approach to ab. Because x of 0 is a, y of 0 is b. So as t approach to t0, x approach to a, y approach to b. So as t approach to t0, as y approach to ab. Then as sy approach to ab, epsilon 1 approach to 0. So this limit becomes 0. And this limit is x prime of t. This limit is s prime of t0. This limit is s prime of t0. And similarly, as t approach to t0, sy approach to ab, and as sy approach to ab, epsilon 2 approach to 0. This limit is 0. And this limit is y prime of t0. This limit is y prime of t0. So 0 times s prime of t0 is 0. 0 times y prime of t0 is also 0. These two terms disappear. What's left is g prime of t0, g prime of t0 equal to f sub x of a b times s prime of t0 plus f sub y of a b times y prime of t0. These two terms become 0. So that's the theorem. That's the proof of this formula. And it can be rewritten as dg over dt equal to delta f over delta x times dx over dt plus delta f over delta y times dy over dt at t equal to t0, xy equal to ab. So g is differentiable at t0. G is differentiable at t0, and that's its derivative. That completes the proof of chain rule. Similarly, this idea works for functions with more than two variables. For example, if w is a function of s, y, z, and x is a function of t, y is a function of t, z is a function of t, then dw over dt, w is a function of t, dw of dt can be rewritten as delta f over delta x times ds over dt, delta f over delta y times dy over dt, delta f over delta z times dz over dt. And if w has n variables, let w be f of s1, s2, sn, where s1 equal to s1 of t, s2 equal to x2 of t, and xn equal to xn of t. Each x is a function of t. Then w itself is a function of t. So use chain rule. dw over dt can be rewritten as delta f over delta s1 times ds1 over dt delta f over delta s2 times dx2 over dt. Delta f over delta sn times dxn over dt. That's the chain rule in general. Next, let's look at some examples. Let z equal to x squared y minus y squared, s equal to sine of t, and y equal to e of t. Find dz over dt at t equal to 0. So let's use chain rule here. So for chain rule, I suggest you use a tree diagram. For chain rule, I suggest you use a tree diagram. So here our z equal to, treat this as a function of f. This z is a function of two variables. Treat this as a function f with two variables, x and y. So z equal to f. F has two variables, x and y. Function x has only one variable, t. Function y has only one variable, t. So dz over dt, look at a branch with t's. There are two branches that has t. So this can be rewrite as delta f over delta x times delta x over delta t plus another branch delta f over delta y times dy over dt. Delta f over delta x, because f is a multivariable function, I use delta, then times dx over dt. X is a single variable function, I write ds over dt, plus another branch of t is here, delta f over delta y, because f is a multivariable function, so I write delta f over delta y, times dy over dt. Y is a single variable function, so I write dy over dt. That's the formula. Then plug in delta f over delta x. I take partial derivative with respect to x. I have 2xy. Take partial derivative with respect to x. I have 2sy times ds over dt. That's cosine t plus delta f over delta y. Take partial derivative with respect to y. I have x squared minus 2y times dy over dt. Take derivative with respect to t. I have e to the power t. Then we try to evaluate at t equal to 0. When t equal to 0, s equal to sine 0, which is 0. Y equal to e to the power 0, which is 1. Then substitute. If I substitute 0 for x, first one is 0. Substitute 0 for x. I have 0 minus 2 times e to the power 0, which is 1. So the final answer is negative 2. Next example. Let z equal to x squared plus y squared, s equal to sine t plus cosine t, y equal to sine t minus cosine t. Find dz over dt at t equal to pi. Find dz over dt at t equal to pi. So here, let's draw tree diagram first. We treat z as a function of x and y. So z is the same as f. F has two variables, x and y. Function x has only one variable, t. Function y has only one variable, t. So dz over dt can be rewritten as delta f over delta x times ds over dt plus delta f over delta y times dy over dt. Then substitute delta f over delta x. Take partial derivative with respect to x. I have 2x. dx over dt. Take derivative with respect to t. I have cosine t minus sine t plus delta f over delta y. Take partial derivative with respect to y. I get 2y times dy over dt. Take derivative with respect to t. I have cosine t plus sine t. Then substitute. When t is pi, sine pi is 0, cosine pi is -1, s equal to -1. When t is pi, sine pi is 0, cosine pi is -1. I get +1 here. S equal to -1, y equal to +1. Then substitute. 2x, that's -2. 2x, that's -2. Cosine pi is -1, sine pi is 0. 2 times y is 2. Cosine pi is -1. Cosine pi is -1, sine pi is 0. So the final answer is 2 plus -2, which is 0. Next, let w equal to ln of s squared plus y squared plus z squared, and x equal to cosine t, y equal to sine t, z equal to 4 square root of t. Find dw over dt at t equal to 1. So, first of all, w is a function of 3 variables. W is a function of 3 variables. So we write w equal to function f. Function f has 3 variables, s, y, z. X has only one variable, t. Y has one variable, t. Z has one variable, t. dw over dt can be rewritten as delta f over delta x times ds over dt. Delta f over delta y times dy over dt. Delta f over delta z times dz over dt. Then substitute. Delta f over delta x. Take partial derivative with respect to x. I have 1 over s squared plus y squared plus z squared times 2x. dz over dt If I take derivative for x, I have negative sine t. Delta f over delta y is 2y over x squared plus y squared plus z squared. Then find dy over dt. dy over dt is cosine t plus delta f over delta z. That's 2z over x squared plus y squared plus z squared times dz over dt. Z can be rewritten as 4t raised to a half. If we take derivative, that's 2 times t raised to negative a half. Then substitute. When t equal to 1, substitute. When t equal to 1, s equal to cosine of 1, y equal to sine of 1, z equal to 4. Then substitute. These numbers are not nice, but we can use calculator and get an answer. I use my calculator, I get 16 over 17. Next example. Let w equal to x over z plus y over z. X equal to e raised to 2t. Y equal to ln of t. Z equal to 4. Find dw over dt at t equal to 1. This function w is a function of s, y, z. If we apply the chain rule for 3 functions directly, I have dw over dt equal to delta f over delta x times dx over dt plus delta f over delta y times dy over dt plus delta f over delta z times dz over dt. But in this example, z is a constant, so dz over dt is 0. Therefore, the entire term is 0. So, an easier way for this problem, an easier way to set it up, we can write it like this. An easier way to set it up looks like this. W is the same as f. F has 3 variables, x, y, z. S is a function of t, y is a function of t. Z is a constant function, there's no variables. We leave it the way it is. We are looking for dw over dt. There are 2 branches of t here. So first branch is delta f delta x times ds over dt. Second branch is delta f over delta y times dy over dt. We get exactly the same thing. But this way has a little less work than this. Use the formula. We first of all find delta f over delta x. I have 1 over z times dx over dt, which is 2e raised to 2t, plus delta f over delta y. The partial derivative with respect to y, I get 1 over z. First term becomes 0, there's no y. First term becomes 0. Second term is 1 over z. Times dy over dt, that's 1 over t. Then when t is 1, x equal to e squared, y equal to ln of 1 is 0, z equal to 4. Then we substitute. I get 1 over 4 times 2 times e squared plus 1 over 4 times 1 over 1, that's 1, which is half e squared plus a quarter. Next example, let z equal to t squared y cubed minus 3t x squared y, x equal to t squared plus 4, y equal to e to the power t. Find dz over dt at t equal to 1. If we set up this problem using chain rule, we can see that this function z has 3 variables, t, x, y. If I treat t as an identity function, x is t squared plus 4, y is e to the power t. Then the chain rule looks like this. dz over dt, there are 3 variables. We write delta f over delta t times dt over dt. And the second variable is x, delta f over delta x times dx over dt. The third variable is y, we do delta f delta y times dy over dt. That's here we use chain rule for 3 variables, t, x, y, where t is identity function t. T is an identity function t. And in this formula we know dt over dt, if I take derivative here, I get 1. dt over dt is 1. dt over dt is 1. dt over dt is 1. So this equation can be rewritten as dz over dt equal to delta f over delta t plus delta f over delta x times dx over dt plus delta f over delta y times dy over dt. Let's simplify the formula. And this way may take too much time. There's an easier way. By using tree diagram. There's an easier way by using the tree diagram. So here we can see that g is the same as f. F has 3 variables, t, x, and y. T is independent variable, so it doesn't go anywhere. T is independent variable, it doesn't go anywhere. X is a function of t. Y is a function of t. Then we are looking for dz over dt. If we are looking for the tree diagram, we have 3 branches of t. First branch is delta f, delta t. Second branch is delta f, delta x times ds over dt. Third branch is delta f, delta y times dy over dt. We get exactly the same answer, but this way we have a little less work. If we do this, we use tree diagram, we have a little less work. Next, let's compute the derivative. Partial derivative with respect to t, we have 2t y cubed plus 3x squared y. That's the first one. Second one, partial derivative of f with respect to x, I have negative 6txy, negative 6txy times dx over dt, that's 2t. The third term, partial derivative with respect to y, is 3t squared y squared minus 3tx squared times dy over dt, which is e to the power t. Then substitute. When t is 1, x is 5, y is e. Use my calculator, I get 5e cubed minus 60e. Next example, let w equal to tx squared y cubed plus t squared y to the power 4 z cubed. S equal to cosine of t, y equal to sine of t, z equal to e. Find dw over dt at t equal to pi over 3. This function w has 4 variables, t, x, y, z. Let's use tree diagram for this problem. W is the same as f. F has 4 variables, t, x, y, z. T is an independent variable. T is an independent variable with different weights. X is a function of t. Y is also a function of t. Z is a constant with different weights. We are looking for dw over dt. This tree diagram has 3 branches of t. We are looking for dw over dt. We have 3 branches of t. So first branch is delta f over delta t. Second branch is delta f over delta x times dx over dt. Third branch is delta f over delta y times dy over dt. Then take partial derivative and plug in. Delta f over delta t, take partial derivative with respect to t. I have x squared y cubed plus 2t y to the power 4 z cubed. That's the first term. Second term, take partial derivative with respect to x. I have 2tx y cubed. The second term becomes 0 times dx over dt. I have negative sine t plus delta f over delta y. Take partial derivative with respect to y. I have 3tx squared y squared plus 4t squared y to the power 3 z to the power 3. Take partial derivative with respect to y. Then times dy over dt. dy over dt is cosine t. Then substitute. We have t equal to pi over 3, x equal to cosine pi over 3. Cosine pi over 3 is a half. Y equal to sine pi over 3. Sine pi over 3 is radical 3 over 2. And z equal to e is constant. Plug in these values. here. Use my calculator, I get 3 radical 3 minus 3 pi over 32 plus 3 pi e cubed over a plus 3 radical 3 pi square e cubed over 36. Next, let z equal to t squared sine x minus e to the power t times y. X equal to t plus cosine of y. Y equal to t squared plus pi. Find dz over dt at t equal to 0. In this function, we can see that z is a function of t, x, and y. If we use chain rule to set up this problem, what do we get? Use chain rule, I first of all treat t as identity function. X is t plus cosine t. Y is t squared plus pi. If I use chain rule to set up the problem, dz dt equal to delta f delta t times dt over dt plus delta f delta x times dx over dt plus delta f delta y times dy over dt. We know that dt over dt is 1. dt over dt is 1. How about dx over dt? Here x is a multi-variable function. So for dx over dt, we need to use chain rule one more time. For dx over dt, we need to use chain rule one more time. Treat t as a function of t. So if we use chain rule here one more time, we have, if we use chain rule for dx dt over dt, I have delta, let's call this function g. Let's use it as x. Delta x over delta t times dt over dt plus delta x over delta y times dy over dt. Because this function has two variables, t and y, we treat t as a constant, as identity function t, and y is a function of t. So I have delta x delta t times dt over dt plus delta x over delta y times dy over dt. With chain rule again to find dx over dt. To find dx over dt, we use chain rule again. So this function can be rewritten as, this function after we simplify, it can be rewritten as dz over dt. That's delta f over delta t. dt over dt is 1. This is also 1. Delta f over delta t plus delta f over delta x times dx over dt is this. Delta x over delta t plus delta x over delta y times dy over dt plus the last term, delta f over delta y times dy over dt. And after we simplify, it can be rewritten as distribute delta f over delta x over delta t plus delta f over delta x times delta x over delta y times dy over dt plus delta f over delta y times dy over dt. That's how we solve it using chain rule. But there are too much work here. If we use tree diagram, I think it's a little easier. If we use tree diagram, it will be a little easier than using chain rule twice here. If we use tree diagram, it will be much easier than using the chain rule twice here. Let me use tree diagram for this problem. Let me use tree diagram. Here, G is the same as F. G is the same as F. F has three variables, T, X, and Y. T is an independent variable. We leave it the way it is. X has two variables, T and Y. X has two variables, T and Y. Y is a function of T. Y has a variable T. Again, this Y also has a variable T. We are looking for dg over dt. In a tree diagram, there are 4 branches of T. We find each one individually and add them up. First branch, delta F over delta T. Second branch, delta F over delta T, delta X over delta T. Delta F over delta X, delta F over delta X, delta X over delta T. The reason I put delta X over delta T here is because X is a multi-variable function. So I write delta X, delta T. This is a partial derivative with respect to T. X is a multi-variable function. I'm taking partial derivative with respect to T. That's why I write delta X, delta T here. Third branch, delta F over delta X, delta X over delta T, and dy over dt. Last branch, delta F over delta Y times dy over dt. The reason I write dy over dt is because y is a single variable function. I'm taking derivative with respect to t. That's why it's dy over dt. Y is a single variable function. So use tree diagram, we get the same thing. Use tree diagram, we get the same thing. But using tree diagram is much easier than using chain rule twice. Using tree diagram is much easier than using chain rule twice. Next, let's calculate the derivative. Partial derivative with respect to t, I have 2t sine x minus e to the power ty. That's the first term. Second term, partial derivative with respect to x, I have t squared cosine t times partial derivative with respect to t, that's 1. The third term, let me put it here, the third term, partial derivative with respect to x is t squared cosine t. Partial derivative of x with respect to y. Partial derivative of x with respect to y. That's negative sine y times dy over dt. dy over dt is 2t. dy over dt is 2t plus the last term, partial derivative of f with respect to y. I have negative e to the power t times dy over dt, which is 2t. Then evaluate. We have t equal to 0. If I substitute t for y, let's find y first. X has two variables, t and y. Let's find y first, then find x. If I substitute 0 for y, y is pi. Then substitute t and x, t and y, we can find x. When t is 0, y is pi. Cosine of pi is negative 1. 0 plus negative 1 is negative 1. Then substitute. T is 0, so this is 0. I have negative e to the power of 0 is 1 times y plus t is 0, this term is 0. Next term t is 0, next term t is 0. So they're all zeros. Answer is negative pi. Next, let z equal to x squared y cubed. X equal to 2t minus 1. Y equal to t squared plus 1. Find the second derivative with respect to t. Find the second derivative with respect to t at t equal to 1. Find the second derivative with respect to t at t equal to 1. So let's first of all compute the first derivative. This z is a function of two variables. F has two variables, x and y. X has a variable t, y has a variable t. So I find dz over dt first. There are two branches of t here, so I have delta f over delta t delta f over delta x times dx over dt plus delta f over delta y times dy over dt. If I simplify, I take partial derivative and simplify, I have, if I take partial derivative with respect to x, I have 2xy cubed. Dx over dt is 2. If I take partial derivative with respect to y, I have 3x squared y squared. Dy over dt is 2t. And it can be rewritten as 4xy cubed plus 6t x squared y squared. Next, we try to find the second derivative. That means I take derivative one more time. This function has three variables. Let's call this function g. It has three variables. Let's call this function g. It has three variables, t, x, and y. So dz over dt is the same as g. Dz over dt is the same as g. G has three variables, t, x, and y. T is an independent variable. X is a function of t. Y is a function of t. So the second derivative d squared z over dt squared, it can be rewritten as, if I take the second derivative, there are three branches of t. I have delta g over delta t plus delta g over delta x times dx over dt, another branch, delta g over delta y times dy over dt. Then take partial derivative, plug in. Delta g over delta t. If I take partial derivative with respect to t, I have 6x squared y squared. Delta g over delta x. If I take partial derivative with respect to x, I have 4y cubed plus 12tx y squared times dx over dt, which is 2, plus delta g over delta y take partial derivative with respect to y. I have 12x y squared plus 12t x squared y times dy over dt. dy over dt is 2t. Then substitute 1 for t. When t is 1, x is 1. 2 times 1 minus 1 is 1. Y is 1 squared plus 1 is 2. Then substitute 6 times 1 times 4 is 24. 4 times 8 plus 12 times 1 times 1 times 4 is 48 times 2 plus 12 times 1 times 4 is 48 plus 12 times 1 times 1 times 2 is 24 times 2 times t is 2. Then use calculator. I got 328 as an answer. Next, let z equal to ln of x squared y. S equal to 2t squared plus 1. Y equal to 3t squared minus 1. Find d squared z dt squared. Find the second derivative at t equal to 1. So we first of all compute the first derivative. Z is a function of two variables. Let's call this function f. It has two variables. This function can be rewritten as ln of x squared. This function can be rewritten as ln of x squared plus ln of y. Then bring 2 to the front. That's ln of x plus ln of y. Z is the same as f. F has two variables, x and y. X is a function of t. Y is a function of t. So dz over dt. For dz over dt, we have two branches of t. First branch, delta f delta x times dx over dt. Second branch, delta f over delta y times dy over dt. Substitute delta f over delta x is 2 over x. Take partial derivative with respect to x times ds over dt. That's 2t. ds over dt is 4t. ds over dt is 4t plus delta f over delta y, that's 1 over y, times dy over dt, that's 6t. Then if we simplify, that can be rewritten as at over x plus 6t over y. This is a function of three variables. Treat this as a function g. It has three variables. So dz over dt is the same as function g. G has three variables, t, x, and y. X is a function of t. Y is a function of t. We are looking for the second derivative, which means the take derivative again with respect to t. We take derivative again with respect to t. We have three branches of t here. So the second derivative d squared z over dt squared. We have three branches of t. Delta g over delta t plus delta g over delta x times dx over dt plus delta g over delta y times dy over dt. Delta g over delta t, take partial derivative with respect to t. I have a over x plus 6 over y. Second term, delta g over delta x, I take partial derivative with respect to x. That's negative at over x squared times dx over dt, take partial derivative with respect to t. That's 4t. dg over dy, take partial derivative with respect to y. I have negative 6t over y squared times dy over dt, take derivative with respect to t. I have 6t. Then evaluate. We have t equal to 1. If I plug in 1 for t, my x is 3. My y is 2. So substitute. I have a over 3 plus 6 over 2 minus a over 9 times 4 minus 6 over 4 times 6. Using my calculator, I get negative 62 over 9. What we learned so far is chain rule case 1. There's only one independent variable. Next, we'll study chain rule case 2. There are multiple independent variables. Let z be a function of x and y. Let x be a function of s and t. And let y be a function of s and t. Then z can be rewritten as a function of s and t. We can treat z as a function of s and t, defined as f of x of s comma t and y of s comma t. Then, since z has two variables, we can try to find the partial derivative with respect to s and t. Delta z over delta s. When we find delta z over delta x, we treat t as constant, take partial derivative with respect to s. So I actually use the chain rule for single variable function to find delta z over delta x. Because I treat t as constant, I'm taking partial derivative with respect to s. So using the same formula here, we have delta f over delta x times delta x over delta s plus delta f over delta y times delta y over delta s. Because x and y, they are multi-variable functions, so I need to take a partial derivative with respect to s. That's why I write delta x over delta s, delta y over delta s. Similarly, delta z over delta t, we take partial derivative with respect to t, treat s as constant. So we can apply the chain rule for single variable functions to find delta z over delta t. Because I treat s as constant, I take a partial derivative with respect to t. So using the same formula, we have delta f over delta x times delta x over delta t plus delta f over delta y times delta y over delta t. We can also set up the chain rule using tree diagram. Z is the same as f. F has two variables, x and y. X has two variables, s and t. Y also has two variables, s and t. S and t, they are called independent variables. Here we have two independent variables. When we're looking for delta z over delta s, we have two branches of s. First branch, delta f, delta x, delta x, delta s, delta f, delta x, delta x, delta s. A second branch of s is delta f, delta y over delta s. And when we are looking for delta z over delta t, we have two branches of t. First branch is delta f over delta x over delta t. Second branch is delta f over delta y over delta t. That's the chain rule for two variable function. You also work for three variable function, four variable function. Next, let's try some examples. First one, let z equal to x squared plus y squared, x equal to s plus t, y equal to 2s minus 3t. Find delta z over delta s. And delta z over delta t at st equal to 2, 1. So z is a function of two variables. Let's make a tree diagram first. Z is the same as f. F has two variables, x and y. X also has two variables, s and t. Y has two variables, s and t. When we are looking for delta z over delta s, we are looking for the branch of s here. There are two branches of s. So we have delta f over delta x times delta x over delta s plus delta f over delta y times delta y over delta s. Then take a partial derivative. I have 2x times 1 plus 2y times 2. Then evaluate. We have s equal to 2, t equal to 1, x equal to s plus t, that's 3, y equal to 2 times s minus 3 times t, which is 1. Then plug in. 2 times x is 6 plus 2 times y is 2. 2 times 2 is 4, which is 10. Next, let's compute delta z over delta t. There are two branches of t. So we have delta f over delta x times delta x over delta t plus delta f over delta y times delta y over delta t. Use chain rule for these two branches. Then take a partial derivative. I have 2x. Delta x over delta t is 1. Then delta f over delta y is 2y. Delta y over delta t is negative 3. Then substitute. X is 3. 2 times 3 is 6. Y is 1. 2 times 1 is 2. 2 times negative 3 is negative 6. 6 plus negative 6 is 0. Next example. let w equal to x y squared plus y z squared, s equal to s t squared, y equal to s squared plus t, z equal to s over t cubed. Find delta w over delta t, delta w over delta s, and delta w over delta t at st equal to 1 comma -1. So here w is a function of x, y, and z. Let's draw the tree diagram first. W is the same as f. F has 3 branches, x, y, z. X is a function of st, y is a function of st, z is also a function of st. So delta w over delta s, we have 3 branches of s here. Using a tree diagram, we have 3 branches of s. First branch, delta f over delta x times delta x over delta s. Second branch, delta f over delta y times delta y over delta s. Third branch, delta f over delta z times delta z over delta s. Take partial derivative and plug in. Delta f over delta x is y squared. Delta x over delta s is t squared. Delta f over delta y is 2sy plus z squared. Delta y over delta s is 2s plus delta f over delta z is 2yz times delta z over delta s is 1 over t cubed. Then we try to evaluate. I substitute 1 for s. S is 1, t is -1, x is s times t squared. 1 times -1 squared is 1. My y is 1 plus 1 squared plus -1 is 0. And my z is 1 over -1 cubed is -1. Then substitute these values. Y squared times t squared is 0, since y is 0. Y is 0. I have z squared is +1 times 2s. 2s is 2 plus 2yz, since y is 0, this is 0. I get 2. Next, delta w over delta t. Delta w over delta t. There are 3 branches of t here. Using a tree diagram, there are 3 branches of t. We find a partial derivative using the tree diagrams. We have delta f over delta x times delta x over delta t. Delta f over delta y times delta y over delta t. Delta f over delta z times delta z over delta t. Then take partial derivative, plug in. Delta f over delta x. Take partial derivative with respect to x. I have y squared, the same as the previous one. Delta x over delta t is 2st. Delta f over delta y, the same as the previous one. 2sy plus z squared times delta y over delta s is delta y over delta t is 1 plus delta f over delta z, the same as the previous example, the same as the previous one. 2yz times delta z over delta t. Take partial derivative with respect to t. That's negative 3s over t to the power 4. Then substitute these values. When y is 0, first term is 0. When y is 0, I have 0 here. 0 plus z squared. Z is negative 1. Negative 1 squared is 1. 1 times 1. Plus, if I plug in 0 for y, the last term is 0. I get 1. Next, let z equal to x, y, s, t. The x equal to s plus t. The y equal to s minus t. Find delta z over delta s and delta z over delta t at st equal to 0, negative 1. So let's draw tree diagram first. This z is a 4-variable function. The tree diagram looks like this. Z equal to f. Z is the same as f. F has 4 variables. S, t, x, and y. With s and t, they are independent variables. We leave it the same. S and t, they are independent variables. We leave it the same. X is a function of s and t. Y is also a function of s and t. So if we are looking for delta z over delta s, we have 3 branches of s. That can be rewritten as delta f over delta s plus another branch, delta f, delta x, delta x, delta s. Then another branch, delta f over delta y over delta s. Then take partial derivative. Delta f over delta s. If I take partial derivative with respect to s, I have x, y, t. Delta f over delta x. If I take partial derivative with respect to x, I have y s t. Delta x over delta s is 1. Delta f over delta y. If I take partial derivative with respect to y, I have x s t times delta y over delta s, which is 1. Then substitute. We have s equal to 0, t equal to negative 1, s equal to 0 plus negative 1, which is negative 1, y equal to 0 minus negative 1, which is positive 1. Then substitute. X times y times t, which is 1. Y times s times t. Y times s times t is 0. X times s times t is also 0. So the answer is 1. Next, delta z over delta t. Delta z over delta t. There are 3 branches of t. So take partial derivative for each branch. Delta f over delta t plus delta f over delta x times delta x over delta t plus delta f over delta y times delta y over delta t. Take partial derivative with respect to t. I have x, y, s take partial derivative with respect to x. I have y as t. dx over dt is 1. Next, take partial derivative with respect to y. I have x as t. dy over delta y over delta t is negative 1. Then substitute. X, y, s is 0. Y, t, s is also 0. X, s, t. X, s, t is also 0. 0 plus 0 plus 0 is 0. Next example. Let z equal to 2s cubed y to the power 4. Let x equal to s squared plus t squared. Y equal to s t cubed. Find the second derivative d squared z, delta squared z over delta t delta s at st equal to 1 comma negative 1. That's the second derivative. In order to find the second derivative here, we need to find first derivative with respect to s, then find the second derivative with respect to t. For this notation, we must read it backward. Find partial derivative with respect to s first, then find partial derivative with respect to t. For this notation, we must read it backward. So, z is a function of x and y. Let's draw tree diagram first. Z is the same as f. F is a function of x and y. X is a function of s and t. Y is a function of s and t. Let's find the partial derivative with respect to s first. So delta z over delta s. There are two branches of s. We have delta f over delta x times delta x over delta s plus delta f over delta y times delta y over delta s. Then take partial derivative and plug in. Delta f over delta x is 6x squared y to the power 4. Delta x over delta s is 2s. Delta f over delta y. Take partial derivative with respect to y. I have a s cubed or y to the power 3. Delta y over delta s is t cubed. Then simplify. I have 12s x squared y to the power 4 plus a t cubed s cubed y cubed. Then we need to find the second derivative with respect to t. Let's call this function g. This function g has 4 variables: s, t, x, and y. Let's call this function g. This function g has 4 variables: s, t, x, and y. So delta z, delta s is the same as function g. G has 4 variables: s, t, x, and y. S and t, they are independent variables. We leave it the same. X is a function of s and t. Y is a function of s and t. We are taking the second derivative with respect to t. We are taking the second derivative with respect to t. There are 3 branches of t. So this delta squared z over delta t delta x can be rewritten as delta g over delta t, that's first branch, plus delta g over delta x times delta x over delta t, that's the second branch. The third branch, delta g over delta y times delta y over delta t, that's the third branch. Then take partial derivative. Delta g over delta t, take partial derivative with respect to t. I have 24t squared s cubed y cubed. That's the first term. Second term, take partial derivative with respect to x. I have 24 s x y to the power 4 plus 24 t cubed x squared y cubed, take partial derivative with respect to x, times dx over d delta x over delta t. Delta x over delta t is 2t plus the third term. Take partial derivative with respect to y. I have 48 s x squared y cubed plus 24 t cubed s cubed y squared times delta y over delta t, that's 3s t squared. Then plug in the values. We have s equal to 1, t equal to -1, x equal to s squared plus t squared, which is 2, y equal to s times t cubed, which is -1. Then substitute. Use my calculator, I get -1632. Next example, assume the function z equal to f of sy has continuous second order partial derivatives and x equal to r squared plus s squared, y equal to 2rs. Find the second derivative, delta squared z over delta r squared and delta squared z over delta s squared. So what should we do here? First of all, draw a tree diagram first. Always draw a tree diagram first. Z is the same as f. F has two variables, x and y. X has two variables, r and s. Y also has two variables, r and s. So for the second derivative, d squared delta squared z over delta r squared means we take partial derivative with respect to r twice. So let's find delta z over delta r first. There are two branches of r. So we have delta f over delta r times delta f over delta x times delta x over delta r plus delta f over delta y times delta y over delta r. Then there's nothing we can do here. We don't know what f is, so I leave delta f, delta x the way it is. And delta x, delta r, I can take partial derivative with respect to r. That's 2r. Delta f over delta y, I don't know what f is, so I leave it the way it is. Delta f over delta y times delta y over delta r. Take partial derivative with respect to r. I have 2s. Then this function, for this function, how many variables do we have? Delta f over delta x. If I take partial derivative with respect to x here, it also has two variables, x and y. If I take partial derivative of f with respect to y, it also has two variables, x and y. So this function, if I call this function g, this function actually has four variables, r, s, x, and y. So let's draw a tree diagram. Delta z over delta r is the same as g. G has four variables. G has four variables, r, s, x, and y. R and s, they are independent variables. We leave it the way it is. X has two variables, r and s. Y has two variables, r and s. So when we are looking for delta squared z over delta r squared, we take derivative with respect to r. There are three branches of r. So here we have delta g over delta r plus delta g over delta x times delta x over delta r. Delta g over delta y times delta y over delta r. So delta g over delta r, I take partial derivative with respect to r. There's no r here, this will become 0. Take partial derivative with respect to r, I have 2 delta f delta x. Take partial derivative with respect to r plus delta g over delta x. Take partial derivative with respect to x. These two functions has x. And we treat r and s as constants. We have delta f, delta square f, delta x squared. If I take partial derivative with respect to x, that's what I get here, times 2r. If I take partial derivative with respect to x, I have delta square f over delta x, delta y. Put a new derivative in the front. Put a new partial derivative in the front. We are taking partial derivative with respect to x. Put a new partial derivative in the front. Times 2s. Times delta x over delta r. Delta x over delta r is 2r. Plus delta g over delta y. Take partial derivative with respect to y. These two functions contains y. We treat r and s as constant. So we have delta square f over delta y, delta x. If I take partial derivative with respect to y, put a new partial derivative in the front, times 2r, plus take partial derivative with respect to y. I have delta square f times delta y squared times 2s. Times delta y over delta r. Take partial derivative with respect to r. I have 2s. Then if we simplify, it can be rewrite as 2 delta f over delta x plus 2r delta square f over delta x squared. Distribute to r, it should be 4r squared. plus 4rs delta square f over delta x delta y plus 4rs delta square f over delta y delta x plus 4s square delta square f over delta y square. And we know by Cross theorem, the mixed partial derivatives are the same. By Cross theorem, they are the same. The mixed partial derivatives equal to each other. So these two terms, they are like terms. I can combine like term. I have 2 delta f over delta x plus 4r square delta square f delta x square plus ars times delta square f over delta x delta y plus 4s square delta square f over delta y square. For the other one, delta square z over delta s square. Take partial derivative twice with respect to s. I'll leave it for you as a homework. It's the same procedure, but it's a long process, but it's the same procedure. Next example. Assume g of s and t equal to f of s square minus t square, comma t square minus s square. And f is differentiable. Show that g satisfies the equation. Show that g satisfies the equation t times delta g over delta s plus s times delta g over delta t equal to 0. Show that g satisfies this equation. So let's prove it. F has two components. Let's call this first component x, second component y. Then g of st can be rewritten as f of s of x of s comma t, y of s comma t. Then delta g over delta s. G is a two variable function. For delta g over delta s, we try to compute delta g over delta s and delta g over delta t to check if they satisfy this equation or not. So for delta g over delta s, let's draw the tree diagram first. G is the same as the function f. F has two variables, x and t, x and y. X has two variables, s and t. Y also has two variables, s and t. So for delta g over delta s, there are two branches of s. We take partial derivative with respect to s. We have delta f over delta x times delta x over delta s plus delta f over delta y times delta y over delta s. Plug in. Delta f over delta x is delta f over delta x. We don't know what f is, so we leave it the way it is. We don't know what f is, so we leave it the way it is. Delta f over delta x. Delta x over delta s. Take partial derivative with respect to s. We have 2s. Delta f over delta y. Since we don't know what f is, leave it the way it is. Delta y over delta s. Take partial derivative with respect to s. We have negative 2s. So that's delta G over delta S. Next, we find delta G over delta. Next, we find delta G over delta T. Again, there are two branches of T here. We have delta F over delta X times delta X over delta T. Another branch is delta F over delta Y times delta Y over delta T. We don't know what F is, so we can simplify delta F over delta X, leave it the way it is. Delta X over delta T. Take partial derivative with respect to T. We have negative 2T. Delta F over delta Y. We don't know what F is, so I leave it the way it is. Delta Y over delta T is 2T. Then we plug in delta G over delta S and delta G over delta T into this equation to see if they equal to 0. Let's plug in. We have T times delta G over delta S plus S times delta G over delta T. That's T times this 2S delta F over delta X minus 2S delta F over delta Y. Substitute delta G over delta X S here, plus S times this. Substitute delta G over delta T. I have negative 2T delta F over delta X plus 2T delta F over delta Y. Distribute T, I get 2TS delta F over delta X minus 2TS delta F over delta Y minus 2TS delta F over delta X plus 2TS delta F over delta Y. And we can see that the first term and the third term get cancelled. The second term and the fourth term get cancelled. So the answer is 0. So it is 0. It's satisfied. G is satisfied in this equation. G is satisfied in this equation. Next, we'll study implicit differentiation. Let's first of all review an old problem which you learned in your first semester calculus. Review this problem first. Let s cubed plus y cubed equal to 6sy, where y represents f of x. Find dy over dx. When we have an equation that mixes x and y together, if you try to find the derivative of y with respect to x, we must use implicit differentiation, which means we take derivative for each term with respect to x. Take derivative for each term with respect to x. Then solve an equation for dy over dx. So let's first of all take derivative for each term with respect to x. I have 3x squared plus 3y squared. Since I treat y as a function of x, when I take derivative for a function of y, I need to multiply by dy over dx because of chain rule. Then on the other side, we have 6x times y. Since y is a function of x, we need to use product rule for the last term. Use product rule for the last term. We treat 6x is one function, y is another function of x. Use product rule. Derivative of the first times the second plus the first times derivative of the second. Then we solve the equation for dy over dx. Then we solve the equation for dy over dx. We have 3y squared dy over dx minus 6x dy over dx equal to negative 3x squared plus 6y. So dy over dx, I can pull out 3y squared minus 6x equal to negative 3x squared plus 6y. Dy over dx equal to negative 3x squared plus 6y over 3y squared minus 6x. If I pull out negative sign from numerator, it can be rewritten as 3x squared minus 6y over 3y squared minus 6x. That's an old technique. Today, I'll show you a new technique to find implicit differentiation. Let me rewrite the equation first. This equation s cubed plus y cubed equal to 6sy. I can always make one side of an equation 0. So this equation can be rewritten as s cubed plus y cubed minus 6sy equal to 0. For any equation, I can always rewrite the equation, make one side of an equation equal to 0. Then let me call this a new function, f of sy. Let me call this a new function, f of xy. Let me call this function f of sy, where y is a function of x. Since y is a function of x, this function only contains two variables, x and y is a function of x, I can treat this as a single variable function. Z of x. Then, how do I find dz over dx? If I want to find dz over dx, let me draw a tree diagram first. Z is the same as f. F has two variables, x and y. Y has a variable of x. If I'm looking for dz over dx, there are two branches of x. I write it as delta f over delta x plus delta f over delta y times dy over dx. Because y is a single variable function, so I write dy over dx. And we know this function equal to 0. 0 is a constant. When I take derivative to the left side, I get this. When I take derivative to the right side, I get 0. Derivative of 0 is 0. So when I take derivative from the left side, I get this. When I take derivative on the right side, I get 0. Now, for implicit differentiation, we try to find dy over dx. So if I solve this equation for dy over dx, I move this term over. I have negative delta f over delta x. Then dy over dx equal to negative delta f over delta x over delta f over delta y. That's the formula for implicit differentiation. If we apply this formula to this example, what do we get? We have dy over dx equal to negative delta f over delta x. If I take the partial derivative with respect to x, I have 3x squared minus 6y. If I take partial derivative with respect to y, I have 3y squared minus 6x, which is exactly the same as what we get. But this formula is much easier than this old formula. Next, let's try some examples. Let tension of xy plus 5 equal to cosine x, where y is a function of x. Find dy over dx. So use the new technique. Let's first of all make one side of the equation 0. I have tension xy plus 5 minus cosine x equal to 0. Make one side of the equation equal to 0 first. And let's call this new function f of sy. Then dy over dx equal to negative delta f over delta x over delta f over delta y. Take partial derivative. if I take partial derivative with respect to x, I have secant square sy times y minus plus sine x. Then delta f over delta y. Take partial derivative with respect to y. I have x secant square xy. Another example. Let ln of square root of x squared plus y squared equal to 4 minus sy, where y is a function of x. Find dy over dx. So first of all, rewrite the equation. Make one side of the equation equal to 0 first. This equation can be rewrite as ln square root of x squared plus y squared minus 4 plus sy equal to 0. Let's call this new function f of sy. And for natural log, this function can be rewrite as half ln of x squared plus y squared. Write it this way, it's easier to take derivatives. Minus 4 plus sy equal to 0. Rewrite ln, make it easier to take derivative. Then dy over dx can be rewrite as negative delta f over delta x over delta f over delta y. Delta f over delta x, it can be rewrite as, if I take partial derivative with respect to x, I have half times 2x over x squared plus y squared. If I take partial derivative with respect to x, I have a y here. That's the top. The bottom, if I take partial derivative with respect to y, I have half times 2y over x squared plus y squared plus x. Then if I simplify, it can be rewrite as x over x squared plus y squared plus y over x squared plus y squared plus x. Next example. Let s cube plus y cube plus z cube equal to 1 minus 6syz, where z is a function of f of xy. Find delta z over delta x and delta z over delta y. So to find the partial derivative, to find the implicit partial derivative, we can also try to use this new technique. I first of all rewrite the equation. Make one side of an equation equal to 0 first. X cubed plus y cubed plus z cubed equal plus minus 1 plus 6syz equal to 0. This expression here has 3 variables. I can treat this as a function of syz. I can treat this as a function of syz. Since z is a function of x and y, I can treat this as function of x and y. Since z is a function of x and y, I can treat this as a function of, I can treat function f as a function of x and y. Then, if I try to find the partial derivative of w with respect to x, what do I get? Let's draw tree diagram first. W is the same as f. F has 3 variables, x, y, and z. X and y, they are independent variables. Z is a function of x and y. z has two variables. Function z has two variables. If we are looking for delta w over delta z, delta w over delta x, we have two branches of x. First branch is delta f over delta x. Second branch is delta f over delta z times delta z over delta x. And we know this delta equal to 0. This equation equal to 0. If I take the derivative on both sides, on the left side I get this. If I take the derivative on the right side with respect to x, if I take the derivative with respect to x, I get this on the left side. If I take partial derivative with respect to x on the right side, I get 0. Derivative of constant is 0. Then, if I solve an equation for delta z over delta x, I have negative delta f over delta x over delta f over delta z. And similarly, if I take partial derivative with respect to y, delta w over delta y, on the left side, I use chain rule here. There are two branches of y. I have delta f over delta y plus delta f over delta z times delta z over delta y. That's left side. And if I take partial derivative with respect to y on the right side, I get 0. Then solve an equation for delta z over delta y. I have negative delta f over delta y over delta f over delta z. Keep this formula in mind. Then use this formula for this problem. Let's use this formula for the problem. Delta z over delta x is negative delta f over delta x. If I take partial derivative with respect to x, I have 3x squared plus 6yz. If I take partial derivative with respect to z, I have 3z squared plus 6xy. Then for delta z over delta y, we use this formula here. I have delta f over delta y. Take partial derivative with respect to y. I have 3y squared plus 6xz. If I take partial derivative with respect to z, I have 3z squared plus 6xy. And using this technique is much easier than doing implicit differentiation. Next, let's try a different example. Let tension of x plus y equal to 1 minus tension of y plus z, where z is a function of x and y. Find delta z over delta x and delta z over delta y. First of all, if we use the new technique, first of all, make one side of an equation 0 first. So this equation can be rewritten as tension x plus y minus 1 plus tension of y plus z equal to 0. Let's call this function f of syz. Then use the formula delta z over delta x is negative delta f over delta x over delta f over delta z. Take partial derivative with respect to x. I have secant square of s plus y. Take partial derivative with respect to z. I have secant square y plus z. It's this function is negative. Take partial derivative with respect to x over the partial derivative with respect to y, with respect to z. Then for delta z over delta y, use the same formula. Delta f over delta f over delta y over delta f over delta z. Take partial derivative with respect to y. I have secant square x plus y plus secant square y plus z. Take partial derivative with respect to z. I have secant square y plus z. Another example. Let z equal to e to the power x sine of y plus z, where z is a function of x and y. Find delta z over delta x and delta z over delta y. So if we use the new technique, first of all, rewrite the equation, make one side of the equation equal to 0 first. This equation can be rewrite as e to the power x sine of y plus z minus z equal to 0. Then we call this function f of s, y, z. Then use the new formula. Delta z over delta x is negative delta f over delta x, delta f over delta z. The variable on the bottom go to the top. Variable on the top go to the bottom. Delta f over delta x, take partial derivative with respect to x. I get e to the power x sine of y plus z. Take partial derivative with respect to z. I have e to the power x cosine y plus z minus 1. Then delta z over delta y equal to negative delta f over delta y over delta f over delta z. The variable on the bottom go to the top. Variable on the top go to the bottom. Then take partial derivative with respect to y. I have e to the power x cosine y plus z. On the bottom, take partial derivative with respect to z. E to the power x cosine y plus z minus 1.